Alright guys, so this is the test 1 review video that we're going to go over. So looking at the review, I broke it up in two parts. One is just a conceptual section and the other one is the problems. So we'll spend more time on the problems, but just getting into the conceptual ideas. It says you should be able to describe motion, identify parts, and draw different types of mechanical waves. So we're talking about transverse and longitudinal waves. So you should be able to identify all the parts and the way that the particles move or vibrate and the actual propagation of the wave, so where the wave travels. So if you remember the Slinky in class, I would say that is a good model for you to remember what we need to know there. You also need to know standing waves on strings and tubes or pipes. So we'll have several problems with that, but you need to know the conditions when it's an open-open or a closed-closed, which is the same as a string. So if you understand the string, that's the same as that. And the open-closed tube is the one that's a little confusing, and we'll have a practice one of those. You also need to know how to create the multiple frequencies that cause the string or tube to resonate. So basically going from the fundamental frequency, which is F1, to whatever the frequency of the mode is. And again, those are all conditions for these different types of tubes or for a string fixed at both ends. You should also be aware of the speed of a wave on a string. So that's V equals square root of the tension Ft divided by the mass per unit of string. So we talked about that. The speed of a sound in a medium, so kind of like the ideas of the denser the medium, the speed of sound generally gets faster, and then same with temperature, like the higher the temperature, the particles are moving faster, so the speed of sound is going faster. Explaining how motion of a source and observer, or both of them, will affect the Doppler frequency, so that's a question that you should be okay with. And then differentiating between constructive and destructive interference when you have waves being superimposed. The other sections of the conceptual part deal with the electrostatic section, so electric force and fields. So talking about the law of signs and the direction of electric forces and fields based upon the law of signs. So if you have two positives or two negatives, or a positive and negative, what would happen? Describing how to change factors to affect the magnitude of electric force and field. So basically looking at the equations for electric force and the electric field, and what would you do to make the force get bigger or smaller. So like the electric force, Coulomb's activity, I always spell this wrong, I think that's right, but the Coulomb's law activity that we did in class is related to that. Principle of superposition for multiple charges to determine direction of electric force, electric field. So that's you got multiple charges creating a force or creating a field, and how would the overall force be? What would the outcome of the overall force be? And then kind of the redistribution of charges when they're touched. So that's like the card example. So we did that game with the cards a few weeks ago, where they represented the positive and the negative charges, and you had a number and they touched. So if you remember those activities, those are things to help you kind of remember and kind of clarify your thinking. So I'm going to jump right in and get into the problems. So in the problem section, it says calculate the speed of a wave if the frequency is 20 hertz and the wavelength is 50 centimeters. So it's just using this wave speed equation, which is V equals F lambda. So V equals F lambda, and if you plug in 20 for, that's the frequency, and 50 centimeters is lambda, but we don't work in centimeters, we work in meters, so we got to convert. So 50 centimeters is a half a meter, and you should get 10 meters per second for that one. So that is the answer to that one. Sorry, put that back. The second problem is like a string. So we had a setup similar to this in class, where we had a string and we vibrated one end and it was fixed, and it produced standing wave pattern. So it says a 3 meter long string has a mass of 0.02 kilograms, and I have a typo, and it has a standing wave pattern with waves moving at 200 meters per second, as in the diagram below. So it says, first off, what is the mode of the wave pattern? So the mode is just counting the number of standing wave patterns that are produced, so that's going to be 6. If I asked you to label these, the nodes and antinodes, again, the nodes are where there is no motion, so these are all nodes. So this is, again, a conceptual question, but you'll have something similar on your test, so I want to make sure you're okay with that. And the antinodes are the parts that are the maximum displacement. So where I'm drawing these lines in, those lines represent antinodes, or A's for antinode. What is the wavelength of this wave? So the wavelength, again, you got to figure out how many waves are on this pattern. So remember, a wave, if you just look at one kind of wave going down, the standing wave pattern is produced from the reflection coming back the other way. So if that's one wave, and then the wave that's reflected goes back this way, you just want to figure out how many wavelengths fit on this string. So there's that. So really, it's let me do one more thing here. I'm going to draw in the equilibrium position in green. So if this is like just the string where it's not vibrating, you would focus on a crest and a trough. So that would be one wavelength, I would say. That far is one wavelength. There's a second wavelength here, and then there's a third wavelength here. So the way that I think about this, if there are 3 wavelengths on a 3 meter long string, to get the wavelength, you just divide by 3 on both sides in this one. So the wavelength of the string is, or of this wave, is 1 meter. So you get 3 wavelengths on the string. So that makes sense. What's the frequency creating this pattern? You use this equation again, V equals F lambda. So if V in this case is 200, and F is what we're looking for, and lambda is 1, because we just said that the wavelength is 1. So the frequency is actually 200 as well. So 200 hertz is what is oscillating the string for this example. If you are trying to find the fundamental frequency, you got to identify what frequency is this. So this is the 6th mode, so this is F6. And for strings or open tubes or closed tubes, F of the mode is equal to just the mode number times the first frequency. So if we divide both sides by M, we'll get the fundamental frequency. So it's 200 divided by 6. So 200 divided by 6 is 33.3 hertz. So that is how many oscillations per second is going on with the frequency that is the fundamental frequency. So that was part D here. The mass per unit length, that's this U constant for the string. So it's mass over L. So it's, again, the mass was 0.02, and you're going to divide that by the 3 meters. And you'll get a number that keeps going, but it's 0.0067, we'll just round to, and it would be kilograms per meter. Finally, you have to find the tension in the string. So that equation that you probably want to use for that is the velocity of the string is equal to the square root of the tension divided by the mass per unit length. So I solved for the tension here by squaring both sides, so it would be like P squared equals Ft over U, and I'm just going to solve the rest algebraically too. So I got U, and I want Ft all by itself, so I'm going to multiply both sides by U. So this is what I need to put in my calculator, and the numbers that I would put in, I'd put in that 0.0067 number, and then I'd multiply that by the speed, which is 200 squared. And if you do that, you'll get the tension is equal to, I got 267 newtons. So that is what I got for the tension on that string. Alright, so continuing on, this one is just a superposition idea. So these two waves are moving towards each other. This one is 3 tall, and this one is 1 tall. When they overlap each other, you would get a wave that's 4 tall when they're overlapped, because you'd have the 1 plus the 3, and you would get 4. So 4 whatever blocks or units or whatever meters this is would be that one. This one is going to the right and this is going to the left. This one is 3 up and this one is 1 down. I might have had a typo on my answer key because I thought this one was 2, but the idea is that they subtract in this one, so you would get a wave when they overlap that is 2 negative, or I'm sorry, positive 2. I messed that up twice now. So this is positive 3 and this is a negative 1. When you add those together you get a positive 2. So when they overlap you get a height or an amplitude of 2 here. For this one, number 4, it says a person sings in the shower, and in the shower basically acts as a closed tube. So a closed tube is acting like the wave on the string. So it's closed, it's a node, so you have a node at both ends. So this is very similar to the string problem where we had a node and a node. And the length of this tube is 2.4 meters. Alright, so that's L. And they sing a note of a fundamental frequency, so F1 is 73 hertz. And we sketched the standing wave pattern that's there. So it says, what is the wavelength of the sound? So to get the wavelength, we need to know how much of a wave fits on this in this tube. So basically this is a half of a wave fits in this 2.4 meter long tube. So if you want the wavelength, you'd have to double both sides. So the wavelength would be 2.4 times 2, which is 4.8 meters. So that's part B. Part C, what's the speed of the sound? So again, V equals F lambda. We're using that equation a lot. It comes up quite a bit, so make sure you remember it. So it's going to be the 73 times 4.8. So if you do that, you'll get 350.4 meters per second. That's the wave speed that you get for this one. In part D, it wants to know, draw the second wave pattern and determine the next frequency that would resonate. So if this is part D. Again, the wave pattern, if you, let me draw the shower again. So if this is the closed tube, you still need a node and a node here. So you're going to need one more node in the middle, so it's going to look like this. And then it would come back. So this is M equal to 1 standing wave, this is M equal to 2. So on the equation for the string or the closed or open tubes, you get Fm equals the mode that you're in times the fundamental frequency. So if we're in mode 2 here, because it's the second standing wave, and we have the frequency is 73, so we're just going to double that. So you'd get 146 hertz. Oops. I said it right. I started to write it wrong. 146 hertz as that next frequency that would cause it to resonate. Alright, the next problem I already have worked out, so that's good. So it says an intensity of 0.1 watts per meter, it should be squared. On the sheet it's squared, but on this one it's messed up. Can cause ear damage, and you're trying to say if the power of a sound from a rock band's amplifier is 85 watts, how far are you standing away from that that speaker? So in this one, you're going to use the intensity equation. So intensity is power divided by 4 pi r squared. Power is 85. 4 pi is a constant, r is the distance, and then I is the intensity, so that's the 0.1 number. So you just solve this out, so I would cross multiply or multiply both sides by 4 pi r squared, so you get 1.26 for 4 pi times 0.1, and then r squared equals 85, and then you divide by 1.26 and then take a square root, and you should get 8.21 meters. So that's how close you are standing next to the speaker. You're only 8.21 meters away. And then for what's the sound intensity level, that's the decibels. So you're going to use the decibel equation, which is 10 times the log of I divided by I naught. I naught, again, is that threshold of hearing. So I is the 0.1, I naught is 1 times 10 to the negative 12th. You divide those, then you hit the log button in your calculator and multiply it by 10. So you get about 110 decibels, which is a pretty big value. Continuing on, 6 is talking about sketching wave patterns. Again, this time it's the open-closed tube, or closed-open tube. So I already drew the first one in as examples, what you're trying to draw. So that frequency is 100. It says that we have to figure out the wavelength. So the wavelength equation for this is equal to wavelength at whatever mode you're at is equal to floor L over M. So again, you got to look at what mode you're in. This is the first mode. The second mode would look like there's a node, and an antinode. So the antinode is the open part, so it would look like this, and come back. And then the third one, to make it work, again, you have an antinode at this end and a node, and then you're going to have two other nodes in the middle. So it would look, and then come back. So this is the antinode. So it's the opening at the open end, and then it's the dots in between. So so for this wavelength, it's 4L over M. So the L is 90 centimeters. So it'd be 4 times 0.9, because we don't work in centimeters. So 90 centimeters, 0.9 meters. And then M in this case is 1. So 4 times 0.9 is 360. No, I'm sorry. I misspoke. 360 is the speed. It's 3.6. Sorry. So 3.6 meters is the wavelength, because remember, for a complete wave you need two standing waves. So this is like a quarter of a wave. This would be another quarter. This is a quarter. This quarter. So that would get you 4 quarters would get you one whole wavelength. So 3.6 is that one. Essentially, this works, the closed open, it's the weird pattern where M can only be odd numbers. So 1, 3, 5. So the second standing wave occurs when you have this pattern, which is basically 4L over 3. So 4L over 3 is 1.2 meters. So I used the same equation. I'm just dividing by M, which is 3 this time, and the next one divided by 5, so that's 0.72. For the frequency, it's still F of M equals M times F1, but this time again it can only be these odd numbers. So it would be 1 times F1, which is 100, so then it would be 3 times F1, which is 300. And then it would be 5 times F1, so it would be 500. So be careful with that. The standing waves, depending on the type of tube or string you have, you gotta make sense out of it. So try to do your best on that. All right, so we're getting into the electric force and electric field portion of this, and I again have the answers underneath these boxes, but just to kind of talk through and conceptually understand what's going on. It says calculate the magnitude and direction of the net electric force on charge B. So this is the charge we care about, which is a positive charge. Charge A is also a positive charge, and charge C is a negative charge. So if we think about charge B, A is going to push or pull on B, and then C is also going to push or pull on B. So if we just think about A and B and we ignored C, we have two like charges. So the force of A on B is definitely going to go and try to push charge B to the right. And then we would look at C on B. So like, how is this negative charge going to impact this positive charge? And again, negative and positives attract, so they're both going to be to the right. So once we figure out the numbers, we're going to add them together to get the net charge, which is going to be the sum of those two vectors going to the right. So the overall one is definitely going to go to the right. So that's kind of like the logic behind it. So without even knowing the numbers or how to calculate anything, you could figure out the directions from just the law of sines. So so I drew that out here. Whoops. And then I used the equations to calculate the electric force. So the equation for electric force, FE for generic electric force, it's between two charges, so A and B or B and C, is equal to K Q1 Q2 over the separation or the distance between them squared. So I just did it here in one line. So for A and B, it's 9 times 10 to the 9th. These are microcoulombs. Micro as a prefix is times 10 to the negative 6. So it's going to be 6 times 10 to the negative 6, and then 1.5 times 10 to the negative 6. And then I need to divide it by the separation or the distance between them squared. So 3 centimeters, we don't work in centimeters, it's going to be 0.03 meters. And then we have to square that. And then again, same idea for 2 centimeters would be 0.02. So I did that equation for both of these. So I did it for A on B, and then C on B. Same constant, 1.5 times 10 to the negative 6 is the same, but this time it's 2 times 10 to the negative 6. And then for the distance, it's 0.02 squared. So you get 50 and 67.5, and when you add those two together, because they're going the same way, you get the net force, which is 157.5 newtons, and it is definitely directed, and I forgot to write this, but it's definitely directed going to the right. So that is that one. And then for the last question on the review, it says calculate the magnitude and direction of the net electric field at the origin. So the origin, I would call this point here, and we're trying to measure the electric field at that point. So the equation for electric field, E is equal to K Q over R squared. So this is the electric field created by a charge at some point away. So we have 3 charges. I labeled them A, B, and C. So the first charge up here is A, I labeled this one B, and this one is C. All these charges are nanocoulombs, so nano is times 10 to the negative 9. So again, a little bit of converting units you got to use. But it's basically just repeating this equation for each one of these charges. They're all the same distance away, so it's going to be 0.5, and that's in the right units already. And you got to square that. And the way that I did it, I looked at kind of the individual electric field created by each of these charges. But I need to kind of just, before I get into calculating it, let me just figure out the directional sense. So this is a positive charge on A, this is a positive charge on B, it's also a positive charge on C. So positive charges create electric fields that are going outward from them. So if I was just drawing a picture for the electric field from A, it would be directed downward, and B would be going to the left, and C would be going up. So so that is the kind of generic picture that I had, just getting the directional sense. So B is the only one that's going in the X direction. A and C are in the Y, and they're going opposite to one another. So whichever one has a bigger electric field is going to dominate and win that directional electric field battle. So for the X direction, let me just get rid of that box. I said EB is equal to 9 times 10 to the 9 times 6 times 10 to the negative 9. So 9 times 10 to the 9 times 6 times 10 to the negative 9 divided by 0.5 squared. So when I do that, I got 216 newtons per coulomb, and again, I said it was going to the left. In the Y direction, I just did the same formula for A and the variable or charge of A, and then for C, which is 2 times 10 to the negative 9. So these equations are very similar. For EA, I got it in the Y direction, so that's a negative 108 nanocoulombs going down, and then for the C, it's pushing up, or the field's going up. Excuse me. So that's going to be 72 nanocoulombs going up, and then because this one's down, I made it negative, and I added them together, and I got negative 36 newtons per coulomb. For the last part, the overall part, I probably won't ask you to do this on the test, or at least the in-class part of the test. But you're just doing the Pythagorean theorem. So again, I drew the picture of the components. So I had negative 36 down and 216 going to the left. I should have drawn a little arrow here, but you get the idea, hopefully. So these two vectors are adding together, and we're trying to get the overall resultant vector and this angle theta. So when I did the Pythagorean theorem with 36 and 216, I got 219 nanocoulombs, and the angle it's going at is 9.5 degrees below the negative x. So that is the whole review. Hopefully that is helpful, me talking through these problems, and good luck, and make sure you ask questions.